everyone. Oh no, class is over. No, class is just starting. Tiffany's asking about moving back the due dates. Let's go ahead and change around those due dates. We got chapter 7 and 8 coming up right here, and we can do the classified ads. So let's change around some due dates. Here we go. Hopping over. Let's put around some changing around some due dates music right here. Great job on the test last night. The test went really well. Right now, the test average is looking like an 80. I wanted to get that like 85, 90 average. It's right at an 80 test average. But how's everyone doing right here? Let's throw out Mubot. You awake? You can give out some points, Mubot. Tiffany, Kennedy, good to see you here. Looks like we might need to re-wake up Mubot. Mubot, wake up. Let's re-wake up Mubot. But we're going to need to change around because of the way, and I think everything then resets next week because we have the fall break. So because we don't get fall break on our Wednesday class, we will actually be resynced with everybody with the lack of fall break. So Canvas content, yeah, let's put the Canvas content. Well, no one's going to do it if we put it on Thursday. So let's see right here. I've got both classes up and going. Let me see this Canvas content. We'll probably do it in class. You know what? We're going to put the Canvas content due Wednesday. And with the Canvas content due Wednesday, we will do Canvas content in class. Everyone knows that's a good way to get some practice. So we should get through 7 and 8 by that. And we'll do it on Wednesday next week. So Canvas content is getting moved to Wednesday. And there we go. Canvas content getting moved to Wednesday now. And then we'll be resynced with the other classes. Yay for resynced. Just the start of this got a little bit odd because we have one less class and they have one more class. So they were a little bit ahead of us. Awesome. Is there homework and quiz still due on Tuesday night? Let's change that around. Chapter 7, I think, should be due then. So we'll look at some chapter 7. Chapter 8 should not be due then. Chapter 7 would not be bad to be due then. BES 320. Yeah, let's do some BES 320. I made the pause to remove the arrows, but it's giving me unexpected brackets. Caitlin, are you on the Discord? If you can send me your code on the Discord, if you can message me the code, send it to me. I'm going to take a look at the due dates right here. On assignment 4. Awesome. Send me that code. Send me your RMD, and I'll pull it up, and we'll take a look. And then Tiffany's got a question here. Thank you so much, everyone, for swinging by. Busy night last night. Woo! I went on a walk, and I came back, and I had like 50 emails. Don't go on walks. Never go on a walk. Going on walks are bad ideas. Okay, good. We have one assignment due next week, and it is due on the Tuesday. And I think that's all right because we will be doing chapter 7 on Monday, and then we have the Canvas content on Wednesday, which we'll do in class, and then we do get a break, a very long break to the 5th to do the next assignment. So we have a good break between assignments. Is the visualization 5 still due on Wednesday night? Yep, I think we should keep that there, and the visualization will be due on Wednesday night, so we should be going that. I moved the Canvas content back, so next week is a bigger week. Like, it is one of those weeks, but we'll be finished up before fall break. So, and then we get a nice rest for fall break. So some people check out and say, it's fall break week, I'm not coming to class. No! Don't do that. Don't check out. Don't check out. And we can start doing some chapter 7 here in a moment, Tiffany. So this will be really great to get some chapter 7 done and to go over the concepts because we will have the class on Monday. Then we will have the assignment. We will finish chapter 8 on Wednesday. Chapter 8 is a much shorter one. It's like a chapter 4. It's a very short chapter. And then we'll do at the very end of class on Wednesday, the Canvas content. So if you're worried about your time utilization right now, chapter 8 on Wednesday, we will do the Canvas content. So we will get that completely done. Got some 474. Yeah, let's take a look. So I think the first question here, Tiffany and Caitlin have a question, then Kelsey has the question. The within cluster sums of squares. Love it. Let's see right here. I think, did you message me? Let's see right here. I think someone else messaged me. Did you send me? You might put it in the general chat. Wait. Okay, wait. Oh, you're sending a picture. Aha. Wait, let me message you here. Hi. Can you send your .rmd? Then we're going to do Tiffany's question next. Can you send your .rmd? Let me get the 320 assignment going right here. And let's take a look at the 320 assignment. And then we're going to come back to a little 201. And then Kelsey will do some 474. So let's check this out. 320, so we did a little resetting of 201 right there. Then we're going to take a look at Caitlin's question 3 on assignment 4. Assignment 4, getting that up and going right here. We will be doing an activity later tonight. So assignment 4, and let's take a look. Question 3, assignment 4 for BAS 320. The picture's not sending. Try or send your RMD file. Send your RMD file. Let's check it out. So question number, let's see right here. Question number 3. On question number 3 right here, use the core demo. Okay, so you're using core demo right here. So here's the biggest thing. So with this right here, when you take pictures, if you're taking pictures of your assignment, here's what I would do. Got some code still up here in my pictures. Here's what I would do if I am working on this. I would take a picture like this right here. And then after I knit, so this is a big tip right here, Caitlin. A lot of people make mistakes on this assignment, especially when they put in the pictures right here. Don't worry about using these. Here's Brian's tips for this question. Don't use these. Delete. A lot of people make mistakes. I've seen so many people forget to put their pictures in and they lose points. So what I would do is I would knit my document. Let's see if this knits. When your document knits, make sure your document knits. Knit early, make sure it's working. So my document in here has knitted, and then I would go down, and this is not an answer to the question. We'll do 1 or 2 of these real quick. But when you go down to this question right here, where we're doing the scatter plots, I would copy my picture. Does that make sense there as a suggestion, Caitlin? If you have or just drag and drop, go to your computer and drag and drop those pictures in. Now, this is not the right answer, but does this make sense right here? Like, knit your document and then insert your pictures, and a lot more people have success with that. You can resource the thing. Yeah, that worked. Yeah, it's kind of the easiest solution because then we're troubleshooting. Like, we could fit, like, if we're in person right now, I could probably troubleshoot and figure out where the file allocation problem is, but much easier solution right here. Let's throw Cliff and everyone some points. So I think that's a pretty good solution. Let's go take a look at that core demo. So here, let's do the first one on this. We're using the core demo to make these plots. A positive linear heteroscedastic. Now, if you are in 201, you were just doing this right here. We want to do, you're welcome, Caitlin, excellent work. You want to make a positive linear. So positive is the what? So who knows right here, 201, 320. 320, this is your class too. 201, you just learned this. Positive is the what of this correlation. Positive is the what of the correlation. Yep, Peyton, we're going to go back and look at some 474. We're going to do a Tiffany's 201 question, then we're going to go to 474. So you got it. Great question, Peyton. So good to see everybody. Positive is the what of this correlation. Good review, like practicing stats topics here to be like, okay, if a correlation is positive, that's telling us the what of the correlation. So if you're in 201, we were just practicing this. This was on your test last night. Positive only tells us the what of the correlation. So when we see positive, I'll do 3 of these and then we'll go do 201. This is a good review of correlation, which goes into regression, which 320 is going to be doing soon, and we're going to look at next for 201. A lot of topics that overlap between courses. Positive is the direction. Linear is the what. 50 points online right here. Who knows what linear is? Positive tells us the direction of the correlation, like negative. Linear tells us the what of the correlation. So I do have a positive linear. Linear is the form of the correlation. Heteroscedastic is an unusual feature. In 201, we only really tell you about outliers, but heteroscedastic means differing spread. So you have right here a heteroscedastic relationship because the thread is, hey, Parker, good to see you here. This is heteroscedastic. Parker, we're like 5 days away from best friends on Pokemon Go. Almost got that. And make sure you open the gift. I've got a lot of experience. I'm pretty high level. So as we get really close right there, make sure you open the gift and get the extra bonus for getting the 100,000. And then use a lucky egg if you want. Or message me and like, hey, Brian, I don't know. I've so many extra lucky eggs and stuff. How about negative nonlinear? So negative would go downward, that's the direction, and then nonlinear is the form, so it needs to be nonlinear. So this is negative nonlinear. How about non-monotonic? I'm going to pause right here, and let's break down what monotonic means. It's your favorite band. Who knows for 100 points in the chat what monotonic means? This one is monotonic. So this is negative, nonlinear, and it's also, it doesn't ask for it, but it is monotonic. This plot right here is negative, nonlinear, monotonic. So why is this monotonic? And then the next one wants us to do a non-monotonic. So what does monotonic mean? What does monotonic mean? Monotonic is your favorite band. It's my favorite way to have us remember it. Monotonic means it goes in only, if you look at this right here, it goes in one direction, your favorite band. So it goes in one direction. So this is a negative, non-linear, because it does not follow a line. It goes downward. Great job, Kirsten, right there. Boom, one direction. Oh, I'm on top chat. And then Tiffany, we got Tiffany's question next right here. Thank you right there. Now I'm seeing the live chat. And it goes in one direction. So if we were to go right here, and then we're going to switch over to one right after this, non-monotonic just needs to be something that goes in more than one direction. And we can see right here that this is not well described by correlation. Is this associated? Yes. It is associated because knowing X tells us something about Y, but it's not well described by correlation because correlation only measures linear strength. So good review. 201, 320, especially 320, your assignments on this. In 201, we're just covering this. So let's go do the 201 question, then we're going to do a little lab for 474. So stay tuned, everyone. Here we go, 201. 201 question right here. Tiffany says, when you get done with this question instead of the one above, researchers collected data on the annual mortality rate of the 20 largest towns and the water hardness, and calcium per million in the drinking water. Let's go check that out. So now we're actually doing some regression. This is the whole name of 320. 320 is a whole course on regression. So if you like regression, we got more courses. So need to go over here to my Pearson. 2 seconds while I get my Pearson booted up. There we go. My Pearson. Replace questions. Now this quiz right here is one of the ones that people are not going to do. This is a tougher quiz. Chapter 8's a little bit easier. But do not let this quiz get by. There's the wildfires. Let's do 2 of these, Tiffany. Let's do 2, and then we'll do a little 474. So we're going to do 2 questions right here from this. This is a tougher one. Trying to find, standardized test ones. That's going to be fun. This is chapter 7, right, Tiffany? Researchers. I know I've done this one. This is chapter 7, right, Tiffany? What? Thank you. I appreciate that. I don't know if I am. It's very, very nice of you. I know a lot of really awesome people, and I'm a huge fan of the Haslam College of Business. Oh, found it. I'm a big fan of Haslam College of Business at UTA. Got my Vol for Life shirt on today. It's Haslam Friday today. Haslam Friday. Got to get down on Haslam Friday. Let's do this. It'll be fun to play some Pokemon Go back at UT. Okay, so what do we have right here? We're actually covering very similar stuff to what we were just talking about seconds ago. Take a look. The display to the right is we're looking at the mortality rate, people dying, and calcium in water. Calcium in water is the hardness of a water, so this is very soft water. -4? Sure. Probably just goes to 0. And this is very hard water. So the harder the water, the lower the deaths. We can't say that causes. Correlation is never causation, and this is a correlation of sorts. We're going to do regression on it in a moment. So definitely negative. That's the direction. Fairly strong negative, linear, towns with harder water. So the more calcium, the harder the water. So towns with harder water tend to have lower mortality rates. Does that make sense, Tiffany, right here? Like the harder water, which is higher calcium, towns with harder water tend to have lower mortality. You see lower mortality here at the higher levels of calcium, which is how hard the water is. That's what hard water is, has calcium in it, because calcium is hard. And so here is the regression equation. Now, a regression equation is as follows. You may have heard, someone may have tried to teach you, and we never want to hear this again. Oh, no. Oh, no. Someone may have told you a long time ago, y equals mx plus b. In statistics, we like to say y hat, which stands for predicted y, equals b0 plus b1x. If you look at where these things are, the x is over here on b1, and that's for each 1 unit increase, making that the slope. So the m right here, which is the slope, is the b1, and that's kind of your first coefficient in a model. More 320 talk to call it the first coefficient. Because you could, if you have two coefficients, you could call this x1 and do b2, x2, and now you have the coefficient for the second x and the second x in the model. But we're not doing multiple regression today. That is multiple regression for 320, which they'll be covering. You can see right here the intercept and the predicted values. So just kind of reorient your mind a little bit here to say we're going to talk about the intercept. And what important thing do you know about the intercept right here? The intercept is when the value of x, and we'll see it over here, the intercept right here is when x is equal to what? The intercept, Snea, good to see you here. The intercept is when x is equal to what? Like if I plug in a value for x, if we were to go to x and we were to plug in a value for x, then we would get the intercept when x is equal to what? And just think why it's called b0. It's not necessarily called b0 because of that, but it's a good way to remember it's b0 because it's when x is equal to what? Think about, oh, it's b0 because that's the intercept. It's when x is equal to this. And you can say that. When x is equal to this, what, b0? It is the x, and on the y-axis, that is correct. And that is when x is equal to what, Tiffany? You are correct. Like if you were to take a value of x and plug it into here, you'd be plugging in when x is equal to 0. Does that make sense? Because that's the y-intercept right there. So it's when x is equal to 0. Does that make sense? I just tried using the function to figure out which rows are column. Yes! Congratulations, Snea. Excellent work. Love that right there. And then the slope right here, I want to think about this slope for a second. The slope right here is for each what in x? The slope right here, Tiffany, is for each what in x? Like as you think about x right here, the slope coefficient, and a good way to remember this, why it's b1, or just a good way to memorize it, the slope coefficient is for each what? Finish my sentence right here. Well, b1 is when we're looking at x and we're talking about for each what in x, we see y change by this. And technically this one would have a negative slope. It is always plus b1, but in this instance it's negative. The rise over the run. So if you look right there, it's b1, so it's for each 1 unit change. So remember, b0 is when x is equal to 0, and b1 is for each 1 unit change in x. Does that make more sense right there, Tiffany, on like a good way to understand how we're using this equation? b0 is when x is equal to 0, and yeah, do it. Snare right there, 100 points. Share that code on Discord. And this is all in relation to x right there. So when you talk about x right here, when x is equal to 0, we get the intercept. And for each 1 unit change in x would be the slope right there, which is b1. So b0 is the y-intercept, and b1 is the slope for each 1 unit change in x. So hopefully that helps you translate the equation you're used to seeing, the mx plus b, into our statistical version. And the y hat is just the predicted value of y, which this would be the line itself. So the line itself is the predicted values. Yep. I need to see in the actual question. Let's take a look at this actual question and see how it works for us right here. We have right here the equation. Now we have the intercept. So where will the intercept go right here? The intercept is b0, right? So if that's the intercept, and it's telling you this is the coefficient of the intercept, that means like the estimate, that's the value of it. This is a lot of output right here, but that's just saying the coefficient of the intercept, the estimate of the intercept. So we're just going to literally take and put that is the estimate of the intercept. And then the slope right here, remember, y equals, or y hat equals b0 plus b1x. So we need the b1, which is the slope coefficient, which is the change per calcium right here, the differences we see at each 1 unit increase of calcium. So this is the slope coefficient right here. And they give a lot more output, which I'm not going to go into too much detail on right now, but that should be the regression equation. Make sure your negatives right here. That's super important. It's a little tiny error, but big error if you forget it. Big error if you forget it. Interpret the slope in context right here. And this is great to practice if we ever do any written responses, which we might have on the next test. for each additional increase in what? Calcium or mortality? So remember, it's always in relation to X. So is it calcium or mortality for each additional increase in calcium or mortality? So is it calcium or mortality for each additional increase in calcium or mortality? And remember how it works. We were just talking about that equation a second ago. And remember how it works over here when we talk about the slope coefficient and we talk about the intercept. It's all in relation to what? So we would say when X is equal to this, or for each additional X. So should it be for each additional mortality or for each additional calcium increase? What should it be? Which one should it be? Exactly. We're just going to decrease, right? Exactly, because it's negative. So for each additional point in calcium, the model predicts a decrease, and you can just think about this right here. As calcium is increasing, we would expect, not saying it will. Yeah, let's take a look at that. We'll take a look. We're going to do some lab here in a second. We're going to do one more 201 question, then we'll go back and do lab. Justin, thank you so much. We're going to do some questions right here. Explain the meaning of the y-intercept. So the y-intercept would be what? So don't look at the answers yet. The y-intercept, which is right here. Ooh, they did not make the pretty graphic. The y-intercept would be when what? When. So just don't look at the answer yet. Just think about the y-intercept is when, and what is that? Is equal to 0. So what would the y-intercept be? We're talking about the expected amount of, can I draw it on here? The y-intercept is going to be somewhere, correct, X, and then we need to give context. You're right on the right track, Tiffany. The y-intercept is probably about here. So that would be the expected what when what is equal to 0. So it might be something like, I think we saw right, it's 17, this right here is 1727 or so. So think about this. What would that be? It's the expected what when what is equal to 0. So we're saying, so try us along right here. I'm going to throw some more points. We would expect when calcium is equal to 0 to observe around 1727 mortality rate. The expected mortality rate when calcium is equal to 0 is around 1727. Does that make sense? Good morning, Roger. Good to see you here. The expected mortality rate when calcium is equal to 0 is 1727. So that is the expected mortality rate. The model predicts that a town with a calcium of 0 would have a mortality rate of this. Because and be very careful, not that it will be that we predict that. Good answers right there, Tiffany. Not that it will be. That says, with the way you've written it right there implies certainty. And then take a look that they're saying predicts right here, that we would predict a town that has 0 calcium. We would expect or predict the mortality rate to be this. We don't want to say it is this. If calcium is this, this will be this, because it's not like a cause and effect. We're saying we would expect this, or the model predicts it. The line says this is what we would expect for these towns. The largest residual was this, so we have to know what a residual is. A residual is how much we miss by. So when we talk about a residual, the formula for a residual is going to be the actual minus the predicted. So there's a little bit talk on residuals right here. If you have right here a point, this is the actual. The line is the line of predicted, and that would make this y hat, making the formula for residual E, which stands for residual, equals the actual, which is the point itself, minus the predicted. This is the formula for residuals, and I like to say a residual wrap. I'm going to change the color right here to red for the residual. And so when we look at what the residual looks like, the residual would actually be this distance right here. Really? So the residual is going to be positive or negative. When you look at that residual right there, is the residual going to be positive or negative? I always like to say residual equals actual minus predicted, the way I remember it. So when you look at the actual, and we could just put in some fake numbers right here to kind of pretend we've got this. So if we were to go right here and go to 0 and go to 20 and go to like 40, what would the residual of that be? Just think about that. What do you think the residual for that would be close to? So look at that point right there and be like, okay, How far is the actual away from the predicted? And the predicted is the line itself. That's the line of prediction. And we have here where the point is actually at. And then the residual is the distance it is away. Like it's kind of like what's left over. So what would the residual be for this when you look at this and you think, okay, the residual is the actual minus the predicted. And residual in notation is E, but I like to call it just the actual. Microsoft Word, we're going to reinstall you this weekend. So what would the residual for this be? It's above it. That is correct. So it is positive. This is the positive residual zone. This is the negative residual zone. I hate Microsoft Word. Positive, negative, and anything on the line would have a 0 residual because you wouldn't miss by anything. So can anyone guess a numeric value of it? Take a moment and guess a numeric value. What does the actual value look to be? So let's think of what the actual value is close to. And then let's think about what the predicted value is close to. So what does the residual look to be? So when you think about that distance it is away, what does the residual look to be? The residual for that point of how far the line misses it by looks to be about what? What would the residual for that one be? What is the numeric value when you solve like, okay, how far above or below the line is that? That's what the residual is asking. The point itself is this far above or below the line. And if it's on the line, it'll have a residual of 0. So what would the residual of that be? Residual is how far away is a point from the line of prediction. So what do you think? How many units above the line is that? Is it on the line? If it's on the line, like this right here, I'll draw another point. This would have a residual of 0. Microsoft Word. You behave. That would have a residual of 0. So we're going to take the actual value. What is the actual value right here, Tiffany? What is the actual value of that observation? That green point right here, what is its actual value? What is the actual Y value of that observation? So what is the actual value of that observation? What is the actual value of it? Like look at its Y value and be like, okay, its Y value is actually this. Its Y value is actually this. So on the Y-axis, what is its actual value of Y? The X won't matter here because we're just comparing how far away it is on its Y value, its distance away from the line. So what is its Y value? Oh no, but look at this graphic right here. So on this graphic right here, what is the value of Y for this right here? So what is the Y value here? So what would the Y value be on this one right here? So when you look at this value of Y right here, what is this value of Y right here? The value of this Y right here is what? Well, no, the exact like numeric value, is it 5? Is it 8? Is it 20? Is it 40? Is it 60? Is it 80? What is the actual value of this Y right here? The actual value of this Y would be what? So we need its actual value. So we only want the Y. So we're only going to take the value of Y right here, which the value of Y is going to be 40. That's the actual value of it. Does that make sense? That's the actual value. That's what it actually is. Now, what was it predicted to be? It was predicted to be what? What was it predicted to be? So what did the line predict it to be? So if you look at the line, which gives us predictions, what was the line predicting it to be? So what was the line predicting it to be? The line was predicting it to be around where? The line was predicting it to be around where? So we have to look and say, what was the predicted value of Y? And these are the things we'll need to solve for our problem. So the predicted value of Y was what? So anytime we get a residual, we need to find the actual and the predicted and find their difference. So the predicted value of Y would be what? According to the model right there that I drew, the predicted value of Y would be what? The predicted value, so we'll just look right here where the line is And then we'll go to the Y. Oh, not also very good guess right there. I'll leave you some points. Great, good guess. It is 20 because right here is the predicted. And so this is the predicted value. And it's just where we're predicting it to be. We're predicting it to be at 20. And so then mathematically, what is the residual? Like mathematically, what is the residual right here? So the residual, which is their difference, is going to be what? So similar. So now we can just find the residual. The residual is mathematically what right here? The residual is mathematically going to be what? Just solve the mathematics right there, and then we can see the residual is going to be 20. Great job, Tiffany, right there. It's going to be 20. And that's the distance that is above the line. So that's 20 right there. That's 20 above the line. So let's take a look at our problem. And I think I want to make sure you see right here, what are the things we need to solve a residual? To get a residual, which I write as R right here, we need two things. What two things do we need? We need, and there's the notation up there for how you actually write it statistically, but I like to say residual wrap to remember we need to get a residual by taking the minus the what. So the notation right there, that's statistical notation, but this is the way to remember it. It's always the blank minus the blank. Now we're going to find that for our problem right here. So we need to understand the theory of what we're doing. So if we ever come to a test problem, we'd be like, oh, residual is just the minus the this. And then we need to find both those things. We need to say, well, what was the actual value of y? And then we also need to say, what was the blank value of y? So what are the two things we need to do to find a residual? To find a residual, we need the, what two things do we need right there? There's the statistical notation. There's the way to remember it. Kind of new and kind of close. So this is the actual, which is going to be where it's actually at. And this is the predicted. So the line itself makes predictions. And you can see that right here. We have a drawing up. So the dots right here, these dots, are these dots right here actuals or predicteds? Are those dots right there actuals or predicteds? A or P in the chat. Are those dots right there in this graphic actual Ys or predicted Ys? Are those dots right there actuals or predicteds? So the dots. Are the dots right here, if we went to its Y value, would that be an actual value or a predicted value? So if you looked over at the mortality rate right there, would that be an actual or predicted? It's an actual, exactly. All of these are actual values because they're the dots themselves. All of the predicteds would come from the where. Every one of the predicted values for this would come from the where. Maybe I should highlight it rather. All of the predicteds, oh, I drew that line. Hint. So all of the predicteds would come from the where. Every single predicted value we get comes from the where. Every single predicted value comes from the line. So if you had a predicted value for this point, it would come from right here. And this right here that I'm showing you, that is that point's residual. Does that make sense? That is the residual right here. This is the value of the residual. If you go from the line, which is the line of prediction, so that's the predicted, and the actuals above it, the blue dot is up here, and you can see that this has a positive residual. So the line of prediction down there is going to make a prediction, and then we are going to subtract, we're going to do actual minus predicted and get the residual. And it's pretty clear to see, hopefully it makes more sense now, that down here below the line, you have things that would have negative residuals. Above the line, you have positive residuals, and anything on the line, like that thing right there, has a residual close to zero. It might be a little bit negative because it's a little bit below the line, but anything very close to the line has a zero residual. If it's on the line, actual minus predicted would be zero. So this will help us with our question, understanding what we're doing with the residual. The largest residual has a value of this, so 83.1. So if we just look at our model right here, if something right here has the largest residual, what does that mean? And actually, it might be that point over there. So if this thing right here has a residual of 83.1, what does that mean? So take a look at the graphic right here. It's probably that point. The town with the largest residual has a residual of 83.1. So what does that mean? Is it A, B, C, or D? And this is, so it says the town had this many more deaths than the model predicted, fewer deaths than the model predicted, and I think it is deaths per 100,000, so we have to make sure to include that context. And so not quite the residual is positive. Yeah, exactly, Tiffany. 100 points right there. Yes. I see what you're saying with R. Yeah, I was thinking correlation. So it's going to be above the line. So that confirms. So the town had this many more deaths than the model predicts. And then we need to give the context. So it had this many because it's a positive residual. And we can see right here, it's probably that point over there. So it has that many more deaths than the model predicts. And on yellow, you see the model prediction. I think we got the right one selected. The hardness of a certain town's water is this. Use the equation to predict. So what we're going to do is we're going to take this right here, the 124, and we're just going to plug it into this equation. So this will literally solve the line for us. We're going to take 124, multiply it by 1492, and then we need to subtract that. Be very careful. Got it right there, and subtract. Do not forget to subtract, and that's our answer. Does that make sense, Tiffany, right here, that we are subtracting? Make sure you're subtracting because this is negative, and was it 124? So we should get something right in about here, and if you trace up, is that 15? Yeah, look, they start their axis here, so that is in the 1500s or so, because they start their axis not at 0, so I was wrong to say this is 0 earlier on. Oh no, it's 0 on the X, but it's not 0 on the Y. So they're starting the Y in a weird spot and just plug in the X. Yep, that's all it is. Just plug in because we're plugging in the calcium and then we're solving. And then this would be a value of Y hat. This is a predicted value right here. So this would be the prediction for a town with a calcium of 124. Round to 3 decimals, look to be good. Explain the meaning of R squared. R squared is the percent of variation in Y explained by the variation in X. So we need to say, and it's 76.4, yep, 76.4% of the variation, that sounds about right, in the mortality rate can be accounted for by a linear model on calcium concentration. That looks to be accurate. Want to make sure I didn't accidentally choose, I think we're good. It's so easy to choose a positive or negative. Okay, we put those in properly. I think we're good. I swear I'm going to get one thing wrong. Woo! Get scared right there. It's so easy to misread a question and just not see a positive, negative, or forget to do something like this, parts per 100 million. But that's a good question. A lot of theory on this question. I know we took a while to do it. We might do some 474 next, but understanding the theory right here is very important. I'm going to write 2 more things, which I hope people take down right now. These interpretations are very important, and the slope interpretation is, for each 1 unit increase in X, we expect Y to increase or decrease by B1. The intercept is when X is equal to 0, we expect Y to equal B0. And the R squared is blank, or R squared percent of the variation in Y is explained by the variation in X. X explains Y. So these right here are important interpretations, but here's what we need to change. 1 unit increase in X will depend on what we're doing. We expect Y, that needs to be context also. Increase, decrease needs to change. And we need to put in the B1, whatever B1 is. So what I'm underlining right here, and this is very important notes, we'll be doing this in class, is the interpretations we'll be using and the context we'll be using. So take this down. This has been a good review. We've done a lot of regression. Tiffany, right now, we've basically done a lot of the chapter. I'd say we've done 70% of the chapter almost, this review right here. So if you look at this on the screen, we could go over here and look at our problem. And let's just keep this up right here. And if we were to interpret on our regression equation those coefficients, we would have, for the slope right here, for each 1 unit increase in calcium, we expect the mortality in deaths per 100,000 to decrease by 1.492, because that's B1 right there. When X, which is calcium, is equal to 0, we expect the mortality rate in deaths per 100,000 to be equal to 1,727.775. And then R squared right here. 76.4% of the variation in mortality in deaths per 100,000 is explained by the variation in calcium in parts per million. So if you notice right here, having these blank interpretations can really help, especially when you get to these interpretations you have to use right here, and it can help you practice for interpreting for the test. So here's our 3 major interpretations, and so this has been a huge review of regression right here. So check this out, and I'll probably send an announcement, say, hey, this is like a mini lecture right here, because we've covered residuals, we've covered the line of prediction, we've covered the slope, the intercept, the R-squared. This is 70% of the lecture or so. And 320, this is good stuff for you all. So let's hop over and do some 474. Let's check it out. And Tiffany, if you have another question, let's do another question here before office hours end. And class is at 12:10. Hour till class. Let's do some activity. 474. Activity time. I think people were wondering about 2A. 2A? Which things were 474 wondering about? Can you do 1C and 474? So 1C and 2A, I think. 1C and 2A, people are wondering about. 1C, 2A. Okay, let's check it out. 2A. Let's start with some 2A. That was, I think, the first one. Then we'll go back and do some 1C. Let me go look at what 2A asks. I think 2A is like a trick question. Love trick questions, right? 474. Oh, wait, there it is. I saw it. Lab clustering. And the question you have for 2A is... Here we go. Let me grab it. Okay. So we'll take a look at this and check it out. 1C, and then we'll do 1C. You got it. Just says referring to K equals 5 means 5 clustering scheme. K equals 5 means 5 clustering scheme. We're doing 5 clustering. We'll check it out next here, Kelsey. You got it. So the question on your quiz is, here's this. Let's drop this in. And yours says the row 155 is one of the outliers. Yeah, that's what we saw. We saw that earlier. It's hard to see it. I don't think I have the data up anymore. Okay. It's hard to see it. It's telling you that. That's really hard to see right there. Like, here, I'll try to make it. It's going to be impossible to see in it which way. No, I can't see it. That's 155, one of those outliers right there that says 155. So it's one of the ones that clusters in way later. So it's one of the outliers right there. It's just a weird point. A little hard to see right there. Sometimes the dendrograms, especially with a lot of data, come out looking kind of crazy. You can try to improve it by decreasing font size and all that stuff, but sometimes they're just a little hard to see. You know what you can do? We could export it. Let me export as PDF and rplot08. Okay. Did it actually turn out decent? No, didn't turn out decent. Dendrograms can look all kind of crazy. Well, it's going to look crazy, but that is 155 right there. That's one of those points that is merging in later into the dendrogram. The row 155 is one of those outliers, and one of the attributes values is the smallest of the corresponding attributes columns in the full data sets. So we want to observe this 155 right here. So how could we go and look at 155? So who could give some hints right here on how we could go and look at 155? How could we look at 155? Let's go and take a look and talk to person 155. What we're working with right now is Kroger data. We are observing what people buy for different categories, whether they're buying, and that's the data process. I want to look at the whole. So there's the whole data right there. And let's go talk to person. Yep. You're close, very close. A few small changes. This is a data frame. Good job right there, Justin, 50 points. Since this is a data frame, close, Kelsey, another 50, or let's go 100 points. Even closer, switch it around a little bit. You're asking for column 155 right there. That's going to go column 155. That's going to get mad at us. But you're super close with that right there. So just switch it over to this right here. And here we are. Now, there's quite a few ways to answer this. And I'm not going to say the answer, but I'm going to kind of show it. So what this question is saying right here is that one of these values, maybe it's fresh, maybe it's milk, maybe it's grocery, maybe it's frozen, is a value that is the smallest for these groups. Like they have the minimum value. So what you could do is you could go, and one way to do this is to go look at the minimum values for any of these variables. So you could go and look at the minimum value for fresh. So the answer is not fresh because they don't have the minimum value for fresh. And you could do this for each one of these, but we have such a cool code for this. There's a lot of ways to do this one. We could go here to aggregate, and we can aggregate all the Y values. No, we don't aggregate. We want to S-apply, smart apply. There's so many tricks. We want to smart apply and take the data frame whole and fun. Is it capital fun? I always get this one wrong. There it is. Yep, that works. So this applies the function min to the full data set, and you can kind of see maybe what the answer is. I'm not going to say the answer once again, but apparently one of their categories is the smallest. One of the things that this person 155 does is the smallest. S-apply is smart apply. It applies a function to smart means it's going to tell if it's a data frame, a list, and it's going to apply the function properly to it. So it's applying the min function to all the columns of the data frame. Cool little thing there, S-apply. Got to keep a lot jumping around your head to be like, what function should I use? But if you don't like the S-apply, there's the good old traditional way of going in here. And we're going to remember that we want to look at person 155 right here. This is the person we're interested in. I'm going to remove the graphic, so hopefully we don't get the graphical error. And we're going to go right here, and we got person 155. Let's just go ahead and look at the data frame. And apparently they're the minimum for one of these. Are they the minimum for fresh? Well, the lowest value for fresh is 3. The minimum for milk is 55. The minimum for grocery is 3. The minimum for frozen is 25. The minimum for detergents is 3. And the minimum for delicatessen is 3. So we're trying to see, they apparently have the minimum value. And this is just trying to understand and know what your data is, like for this cart, for how much they spend. Does that make more sense, Justin? I didn't say the answer, but I've kind of made it clear a few times on what the answer is. I don't want to say what the answer is, but one of their values should be the minimum right there. And then we'll look at Kelsey's question next. But does that make sense on how I'm able to observe person 155 and kind of go through here and see, you know, if 155 were to appear at the top of any of these lists? So yeah, I think you might have caught the answer right there as we went through and tried to see that they have the minimum value for one of these groups right here. And we can observe row 155, and then we could do it via code, or we could just go old-fashioned and observe it ourselves. Especially for huge data sets, if you have like 100,000, 200,000 rows, and even sometimes just even manipulating it visually could take a lot of memory and time. It might be easier to use like a function like sapply right here, which is going to find the minimum for each column. So this is the probably better coder way of solving it. And you could probably do this. Yep, there you go. That's a good way to figure out the answer. Let's go back to the main screen. That's a good way to figure out the answer right there. I was like, yeah, we could probably just check it like logically. Do a logical check right there. Logical check. So logical check would run it for you and just figure it out for you logically. Because I mean, if there is an answer, we can just logically look at it. I just saw that last second. I was like, why not just do this? Just figure out if it is which one is the minimum and run that. Not wait, and careful with your witch. You could pull a witch and then call names on the witch. That would show the answer then, but I think if people are catching what I'm throwing, then you see like, yeah, I got it. Let's look at that 1C. What does 1C say on the assignment? 1C is talking about requires nulling out, enter the values of the within cluster sums of squares where k equals 5. The fifth element of the within cluster sum of squares, assuming you approach this way. Okay, wait. The value of the within. Oh, okay, yeah. Enter the value of the within cluster sum of squares. Yeah, okay, yeah. So let's go take a look at that. I'm making an elbow plot here. Let's go do this. So a very important thing. Yeah, I had a pretty good day today. It was Tuesday was a crazy day. Not fun. But today's going much better. It was, and then we had the test, and the test went all right last night. Test went pretty well. Pretty happy. 80 on the test, I'll take it. Just don't. 201, please don't say fall breaks next week. I'm just gonna take the whole week off. No, we're a full week of class next week. We have all classes next week. We don't have any time off next week. I mean, I'd love time off, but we don't have it. I have the formula on how to make the elbow plot. Just confused to create the... So if you have the elbow plot, this is going to be a little quick right here. Then we can do more 201 if 201 wants. If you have the elbow plot, so you stored the object into... So since you're already there, I might just show you what you need to do. So Kelsey, you've already created your elbow plot, right? And you were storing your things into your in the KME algorithm. No classes on Friday. No class on Friday. I love no class on Friday. Where is it? I can just go do it. Run the for loop. What did you store your object into? Did you store it into like... Did you store it into like this? Does your code look something like this? Yeah, if you have this. So... This is not the answer. Not answer. Talking. Theory. And this is not the answer. And then, well, sure. There we go. Plot too big. This is definitely not the answer. There we go. Look at that one. This is an impossible elbow plot because it goes up here at the end. Oh yeah, exactly. This elbow plot is not possible because it goes up at the end. So maybe I'll make it look a little bit better right here. 34. No, put this to 38. 34, 33, 32.8. Sure. So this is kind of, we've gone along and we've made our elbow plot. Once again, I'm just talking theory right here, and this is more likely. And so this is actually a pretty good elbow plot right here because it kind of goes down. Remember your classic, bad elbow, good elbow, impossible elbow. Bad elbow because there's no clean elbow to see. Good elbow, this is going more towards a good elbow right here because we're seeing the elbow right here of the elbow plot. And then impossible elbow, it can't go back up, so we don't have elbow plots increasing the variation with the increase on the clusters right here. So this is the amount of clusters we have, whether we're doing 1, 2, 3, 4, or 5 clusters. So really what we're going to look at for this question is the within clusters on 5. Is that making sense right there, Kelsey? We want to find how much within cluster sums of squares there is using the 5 clustering scheme. And if anyone's confused, we did this one fully during class. So if you're pulling from this, the within clusters on the 5, you should find out how much within cluster sums. Yep. Awesome job, Kelsey. Throwing out some 50 points on that right there. Like you're right there. If you have the code, then you just need to go and say, well, how much within cluster sums of squares is there at 5? If you've got your vector created, you need to for loop this to create it. So please check out class where we did run this for loop and created the vector. You're not going to create it by doing what I did. I'm just talking the theory on how the elbow plot is created to analyze the within cluster sums of squares. And this is just how tightly packed the points are. We want the points to be tightly packed. You got it. Awesome work right there. What questions are there? We can talk more theory, whatever people want. Let's go back to the main screen. And Kelsey's got it right there. That was a quick question. As long as you have it. What are people wondering? 201, 324, 74, 475. It is your time to ask questions. Anything you're wondering about. Great job today, everybody. We had a big, we had a 201 lecture basically in here. Let me know your questions. I keep getting calls from what is called account services. Trend alert. Oh, it's Pokemon Go saying trend alert. What do you think about Fashion Week, Parker? Sunlink. Oh, wait. Can we do... Yeah! What was your question again, Tiffany? Your question was which one? Classified ads. Okay, awesome. Sorry, I missed that one right there. Classified ads in a local paper used to sell cars. Let's check it out. Yeah. Let's do those classified ads used to sell cars. Classified ads used to sell cars. Boom, we got it. Here we go. Let's check out some classified ads. Thank you so much, Tiffany. Throwing out some points right here. Oh my gosh, gonna change my lights back then. Here we go. So we got some classified ads used to sell cars, and we get some data. We love data. Now you can actually see this has a what relationship. If you look at it as the age of a car increases, what is happening to the price? This is age going up, price doing what? As the age increases, because it's going from 1 to 13, price is decreasing. So that eliminates one of these graphics right here. This graphic has a positive relationship, so that is not correct. These have negatives, and now it is tough to figure out which ones it is, but let's see right here. We can probably visually do it. We have to find the correlation. So we're going to go ahead and use jump. We can maybe visually do it. We have to pick between these two. And I will say this, do zoom in on these, because you can see there's 3 cars with 9 years of age right there. And there's 3 cars. It's very hard to see, but that's 3 cars right there. You got to be very careful. You got to zoom in on them. 2 1 2 2 1 2 2 1 2 1 1 2 2. Is that 2 cars right there? It might be 2, but they'd have to have the same. So 3 years of age. Let me look at the data set again. That is really close. 10985, 109. It might actually be that one. Oh, this one's also close. It might be that first one, because this one looks to have too much difference. And these would suggest that those are close, I think. And then this one has a small jump right there. So the car with 2 years of age would need to be a little lower. And the car with 2 years of age is a little lower. Okay, so we are able to visually figure it out. This is because the car would... Does that make sense, Tiffany? This is a tough one, and I'm visually checking it out. But the car with 2 years of age is a little bit lower than the cars with 1 year of age and the cars with 3 years of age. And so when I look at the car with 2 years of age, do you see how it's a little bit lower than the cars? And that's 2 cars. That's very hard to tell right there. But that is 2 cars. It's because it's a little thicker. If you can tell how that one looks a little bit thicker than that, there's actually 2 cars right there. Just the way that's so hard to tell. But there are 2 cars right there with very similar price. And then the car with 2 years of age is lower. And we saw that by observing the data right here. The data shows that the car with 2 years of age is a little bit lower than the cars with 3 years of age. We do not see the pattern here where a car with 3 years of age sold for less than the car with 2 years of age. So it does confirm it is this graphic. Now we are going to need to jump for this because we're not going to do correlation by hand. We're going to go right here and copy the data to the clipboard and hit Command-C or Control-C. So hit Control-C on a PC or Command-C on a Mac, and then go over to Jump. And inside of Jump right here, you want to go to File, New, Data Table. File, New, Data Table. It'll be up at the top on a Mac. You have to go to the top, or on the Jump window at any point, you can go to the very top, or hit Control or Command-N. Now, don't click inside of it. Don't click inside of it. Since there was column names when we copied, we have to paste with column names. I noticed that there was column names. It said price, and then it said age. So you have to paste with the column names. If it's not blue, it's not quantitative. This right here is incorrect and will not analyze properly because it thinks your data is categorical. So if you see this, start over. You've made a mistake right here. How to copy paste, make sure to hit Control-C or Command-C. So on a Mac, hit Command-C. On a PC, hit Control-C. And then once you get to Jump, after copying it from here, so you want to go right here, click on the data, then click on this little box right here, copy to clipboard. Once you've copied to clipboard, hit Control or Command-C. Control-C on a PC, Command-C on a Mac. That will copy it to your clipboard. Then go over to Jump, and inside of Jump, go to File, New, Data Table. That's File, New, Data Table. Once you're in a new data table, do not click inside of it. Very common mistake. And since there was column names, we're going to go to Edit, Paste with Column Names. Very important to paste with the column names. When you paste with column names, you will see the data is quantitative. If you forgot to paste with column names, please start over. There is a way to fix this, but it's a lot more work than starting over and pasting with column names. So don't try to fix this. It takes more work to fix than it does to start over. So here's where you should be at with the data copied in with the column names at the top, and make sure these are blue, which means they're quantitative. Once again, we need 2 quantitative variables to do regression or correlation. So this one is asking us for the correlation at some point. So I'm going to go over here to multivariate methods, multivariate. With multivariate method multivariate, I can select both of these. You can just double click them if you want and put them in the Y columns. This will get us a correlation matrix. Here's the correlation matrix, and also we could confirm our graphic here. Please note how we have the 2 points, and remember how we saw the 1, 2, 3, 3 right here? These are the 2 points right here, and it is hard to tell the difference between these graphics, but you see how this has a small dip right here, like goes down then up. Third Pokemon of all time. Oh, it's gotta be Charmander, come on. My first Charmander, everyone's first Pokemon's the best. And then this one doesn't follow that pattern. Little hard to tell right here, but this one goes down, up, makes like an L like that. And then this one does not go down, up, makes that L. And then this one goes down, up, and ooh, what? Let me look at it. Want to make sure we got the right. Oh, because it's this one. Oh, I was looking at the wrong one. It's this one right here. This is when the age is, I was like, something's weird. This one goes right here down, makes like a U shape right here, and then it has another U shape right here. So we gotta look for the 2 U's. U like that, and U like this. So there's the U like this, there's the 1 U, and there's the U like this. And on this one, you wouldn't have that. That's not a U, and that's not a good U. Tricky to see the difference, but it's very small, very precise. Describe the association. It's definitely negative, goes down. Is it linear? Oh, I'm going to say it's linear. Don't you tell me that that's not linear. It's pretty linear. And it's pretty strong. We can tell the strength of the correlation or the association by going down here and look at the correlation, and it's negative 0.9455. That is strong correlation. That is very, very strong, and it looks like a line would go through the data pretty well. They're just doing it on XY reverse, but that's very, very strong. Do you think a linear model is appropriate? QQ, straight enough, no outliers. And the last one is plot doesn't thicken for this chapter, a 4th condition. So I'm going to say definitely yes, because it doesn't matter that they've been randomized. No, they haven't been randomized. So we have 2 quantitative variables. It's a straight relationship. There are no outliers, and they're going through that right here. Compute, the software says R squared is this. Oh, awesome. Yeah, I hope and we're doing regression right now. We were talking about residuals a moment ago, Connor. Thank you so much, Connor. 100 points, Connor, swinging by right here. So it wants the correlation to 3 decimals. So here's what you could do, and here's where mistakes happen. This is, once again, teaching to the test moment. If we have R squared, how can we get R? Now, I did solve this using jump, so you don't actually need jump for this. But if you have R squared, how could you get R? Now, be careful. This is where a mistake happens, and people make the same mistake on the test. If you have R squared, how could you get R? If you have R squared, how could you get R? You could take R squared and do what to it? If you have R squared, how could you get R? Just think, if you have R squared, to find correlation, which is R, you could do what to it? And this is where mistakes happen. So to find R, you would do what here? So this is R squared, which is correlation squared in this instance. To find R, we could just take R squared and do what to it? So how would we then find R squared, R from this? This is R squared. So how would we then find R? Good test question right here. I like to pause on things that we've definitely put on test before. Rudette. Exactly. Like there, Connor earning some points for everyone. So here's the problem, though, and you are correct. You are correct. So, but is this the correlation? Here's a hint. Put it next to this graphic. Is this the correlation, yes or no? Is this the correlation, yes or no? And you are correct to take the square root. And then a lot of people say, well, then how would I know? And then you say, so when you square root it, what should you then look at after you square root R squared? Because in technical mathematical terms, when you square root something, it's plus or minus, and that is true. So how would we know it's minus? Connor, great work right here. Connor guys is down. Connor's dropping some hints in the chat. I love it. How would you then know? Like you would know it's negative. Why? Because the direction of the correlation or the line itself is negative. So then we know this is negative. So when you square root it, you must make sure to look at or compute or, just double check, make sure it's negative, and you're like, okay, this has a negative relationship. So since it has a negative relationship, we need to make sure we put here the negative before it and then round to 3 decimals. Now we also, is that going to round up? It does. We also computed it using jump. And so we could, and that does round up right here. Exactly. And you see negative 0.9456 because it does have a negative direction. Explain the meaning of r squared in the context. Remember, we took notes on this earlier. So when you have r squared, it's blank percent of the variation in y is explained by the variation in x. So blank percent of the variation in what? So 89%, I'm rounding it. 89%, great work right there, Tiffany. 89% of the variation in what? Plug in the things right here. Cross-validation algorithm on a time series instinct. Are you running, we've been using, Connor, I'll show you the book we've been using. We've been using the FPP3 book. And what kind of cross-validation are you running? Because there's an even better cross-validation that he suggests that's more modern. And it's like a one step forward cross-validation. It's a, if you are predicting one step forward, he uses a, everyone knows Connor right here. So I'll interpret this right here, but I should show you, I'll show you here that next. We got a little bit of time. We'll finish this question, then I'll show you that, Connor, because he goes through a certain type of cross-validation that he uses, and you could take a look at trying to do that for yours. It might be quicker. Yeah, it's like a rolling cross-validation, exactly. And he does that in the FPP3 book. So here we are, 89% of the variation in price, which is the y variable. 89% of the variation in price is explained by the variation in age right here. Oh, you're doing rolling? There you go. You know what's up. So a linear model on advertising accounts for a linear model on age. There we go. Accounts for 89.4% of the variation in price. We're creating our model on age. Our model is made from age. That's the X variable. And the model is explaining 89.4% of the variation in price. I don't like the way that's written. It's a little tougher to read right there. I would just say 89.4% of the variation in price is explained by the variation in age. Why doesn't the model account for 100% of the variation? This could be one of the few questions I miss. We're going to say some not today, my Pearson. Let's make this not happen today. The data cannot contain more than 10 points. What? You ever hear an answer like that, Connor? The data cannot contain more than 10 points to have a model that explains 100% of the variation. Nah. Just put in more X's and you'll get an R squared of 100. Other factors, that does sound like something reasonable. The age are rounded to years, but should actually be in terms of months. I mean, that's just the way data goes. It's impossible. Oh, I think they changed this because I used to have qualms with this question where it could be multiple answers. You can definitely get an R squared above 90%. You can get an R squared up to 100% easily. You want your data more accurate, like the precision of your data would be better. But that goes to the precision. Yeah, it'd be cool if they had a higher precision on their data. Other factors is definitely it. There we go. They changed this question because they changed one of those answers because I used to debate. I think it used to say like it's impossible to get an R squared of 100%, and then some statistician person must have been like, "Hey, you can get R squared 100% pretty easily. Just make a model that is a saturated model. Just put too many variables in your model." So yeah, don't do that. Don't put too many variables in your model. Great job, Tiffany. Excellent work. Keep working, and we might have time for one more right here. I'm gonna show Connor something real quick. Connor, if you haven't checked this out, FPP3, I might have sent you this, or maybe, I don't think you sent me this. But this guy's book right here, this is Ron or something, I forget his name. Let's go to the main screen. Here we'll see who the guy is. Rob Heinemann. It's this gentleman right here, has this free book online for time series and goes into the cross-validation and everything. So we don't want to start, there we go. There we go. Validation. Oh, really? Nope. I know he does validation. Time series cross validation. It's got a dash. There we go. There's the regular old, and there's the look forward. Goes through the cross validation, talking about how it's done. That's rather short on it, but he shows TSCV there. So are you using the TSCV function? I was trying to turn this into a much better function. But he goes through and shows how to do it right here. I'm running a combination model consisting of an ARIMA, TBATS, single layer neural net, STLM, theta M, and seasonal naive. Oh, seasonal naive, nice. Yeah, you're running a combination model. Do you want to send me? No, you probably can't send me the data, maybe, but do you want to send me that right there? So are you using like Carrot Ensemble? What package are you primarily using to make your combination model? Is because you're ensembling, right? So what are you? Yeah, Tiffany, let's do that. The wildfire one next. You got it. So what package are you using to like ensemble those? To do a combination of those? That is complex. Yeah, definitely. Connor, I should have you swing by and talk to my class. We just finished off talking about time series. I know, right? No, Connor's in the practice of doing it. We just got through time series graphics. We're going to start some time series decomposition soon right here. But I love all the graphics we're getting right here. So we just went through and talked about the different graphics we have right here. So we can correlation, good stuff right here. Lag plots. We went over lag plots last class. We went over autocorrelation last class. We went over the ACF last class. Forecast hybrid. Is that does that go into tidy? Are those tidy capable? I don't know if they are. But we went over all this last class right here. So we've gone through chapter 2, working with them Tisbles. But I haven't used the forecast hybrid. I'm not sure. Yeah, we'll have to take a look. There's so many packages. And yeah, I don't know if he does any blending of models like that. But Connor, you're doing some complex stuff. Love it right there. Let's go take a look. Last question of the day. Tiffany, great questions right here. Connor, I feel like I should have you swing by the class, Connor, because you are doing some really complex stuff. And it's kind of what pushes you. So Connor, let me ask you this. Are you doing things above and beyond what Seaver taught in the classes? So I truly believe this because I think I know the answer. Are you doing things, because Connor works with time series data every day. So I have a feeling, Connor, because what you do when you do this stuff is you go look for the latest and greatest stuff. And you're like, well, let me go get the best stuff out there and use that because it's going to make, yep, exactly. So you're pushing the boundaries, Connor. And we just need to keep having more conversations to help me push the boundaries on what we're doing. And then we just have to get there, because do you think you would have understand what you are doing at the end of time series with Seaver? And I'm going to load up Tiffany's question right here, because it takes time. Connor, amazing student. And it just takes time with these things, like to understand the combination model right here, the ensembling it looks like you're doing, and multiple models, and ARIMA, TBAT, singular neural nets, got STLM, got so many things right there. Theta M, seasonal naive. We'll be doing seasonal naive very soon. Seasonal naive, not too bad. Seasonal naive is nice and easy. You just predict whatever it was last season. Psh. Psh. Seasonal naive. No, it's a good model, though. It's a good model. It's a good basic starting point. It's very good. It's very simple to understand, very good, and that's some of the greatness of it. And it makes sense. What are we going to have this year? I had a great basic understanding after Seaver. Yep. You get that base level, and you build on it. Like you did ARIMAs, I'm sure. You obviously did the naive and the seasonal naive and the mean and just different basic models. And then you build upon that. And then neural nets. I don't think we get into much neural nets. But yeah. Wildfires have been declining. Let's go check that out. Here we go with the wildfires question for 201. Let's go take a look. The number of wildfires in the country has been declining. A scatter plot of the amount of land in millions of acres lost to wildfires is shown to the right. Complete parts A through parts E. So the dependent variable is land. I hate the way they're saying that. That's the Y. That's the response, the Y variable of interest. The X variable right here is years since 1982. Good year. And we see right here an R squared of only 22.2. And this is the residual standard error, not something we talk about much. 320 will learn that is the typical miss the model makes, which is the uncertainty in the ensembling and seasonal naive mitigates. Oh, really? Connor, yeah, let me know about that. Because the ensembling, yeah, because then you're having like a voting together where all the models are coming together and not pushing too much of one model's information through to overfit. So yeah, that perfectly makes sense right there when you have things working together. Have you tried some boosted models? A little boosted? A little tune in that model? Here's the coefficient of the intercept. The coefficient of the intercept is where it hits. You can see it looks, they're making that very tricky. That looks to basically be 3. And then you see the rise over the run, which is B1. So this is for each 1 unit increase right here, the year right here. So that's for each 1 unit increase we're seeing right there. That is the B1. So this is the B0, this is the B1, and you should know how to write the equation. If you're just watching this question, take a look from earlier in this video where we went through and talked about how the equation is written for the predicted value of y using B0 and B1. Do you think the relationship is appropriate? Oh, you got to hate these subjective questions. These are the ones we could miss. Okay, a lot of subjective. Do you think the model is appropriate? That looks better. The relationship is straight enough. Does it follow a straight line? Yes, mostly. Let's look at the nose. The linear model does not pass through any of the data points. That doesn't matter. The model doesn't have to pass through the data points. The model needs to kind of, the points need to be around the model. So the points do look to be around the model. The line looks to go through the middle of it. So that is a wrong no answer. They're too spread out to be modeled. What matters when it comes to linear is, do they follow a linear pattern? So the relationship looks to be straight enough. So this will be QQ, two quantitative variables, straight enough. These aren't really extreme outliers, and none of these mention outliers, so I'm not too concerned about these being outliers. It looks to follow a straight line. We don't want them to be so spread out, but the R-squared is 22%, which is actually not that bad. The correlation, like 22 doesn't sound that good, but the correlation right here is actually about 0.5. So this actually has a moderate correlation. It's a bit spread out, but it's all right. When we look at the slope right here, the slope is going to be the year variable right here. That's the coefficient of the slope. So for each 1 unit increase in year, so every year past, there is an increase to the loss of land by 1.35. The amount of land damaged by wildfires increases by about 1.5 million acres per year. That sounds about right. Has not remained constant and is not decreasing because it's a positive right there. So the slope is positive, so it is increasing. Can we interpret the intercept? What does this 0 represent? What year does that 0 represent? What year does that 0 represent? What year does that 0 represent? That 0 would represent what year? So if we look and we see 0 right there, look what the x-axis says. Does the 0 have any meaning? Sometimes the intercept is meaningless. Good note for the test. A meaningless intercept could be like if we're predicting someone's height and we use their weight. And if we say someone at weight 0, well, then that's meaningless because you can't have a person at weight 0. But this is years since 1982, so the intercept would be what? And this is actually a time plot, so we could do time series on it. So this right here, years since 1982, the intercept would be what? Like this right here is the value. Well, so we're just concerned about, does the intercept have meaning? So if I say at 0, which years since 1982, at 0 years since 1982, so we could go to our interpretation. Here's the intercept interpretation. When years since 1982 is equal to 0, we expect the land loss to wildfires to equal to 3 million acres or something. So this right here, 0 years since 1982, would mean we're predicting for what year? This means this is the prediction for what year. If we say 0 years since 1982, this 0 represents our prediction, which is this value. This is the actual. This is our prediction for what we would expect for year what? Because it's 0 years since 1982. This is what we would expect and what we would predict when the year is equal to. It's what we would expect and what we're predicting for a land loss to wildfire when the years are equal to what? Because it's years. Hey, what's up, Rose? Good to see you here. Oh, Rose, swing back by. Awesome, Rose. Since it's years since 1982, we'll throw 50 points for Rose showing up. Then this would be the prediction at 1982 because it's 0 years since 1982. 0 years since 1982, that's 1982. So this does make sense. Yes, because it represents the amount of wildfires starting at 1982. So that's what we would expect at 1982. What does the standard error represent? This is a little complex right here. And they kind of make it a little bit easier. This is quite large right here. So we're just looking at the model's prediction errors. So when you look at this right here, it's just talking about the errors the model makes. I think this is the only like tough one that we don't go into too much detail on, but it's just asking, is there a lot of error in this model? Or is there a little bit of error? If the standard error, which is what this is, was smaller, then we would see the points closer around the line. So basically, the only thing to really look at right here is that there's a lot of error or there's a little, and we won't go into too much detail on the standard error. Interpret the R squared. 22% of the variation in the acres damaged can be explained by the year. I think that's correct. 22% of the variation in the number of acres damaged by wildfires can be accounted for by the model, but by other factors such as... No. The model accounts for it. They're just adding in extra right there. They shouldn't add in extra. So why are they adding in extra? They changed this question on me. Make these little changes. There's other factors. That would be the coefficient of non-determination, that there are other things not accounting for this. And I didn't know that accounted for still here. For a long time, R squared is the coefficient of determination. 1 minus R squared is the coefficient of non-determination. So they're kind of getting into that down here, that there could be other factors. But we know that 22% of the variation in the land destroyed by wildfires is explained by the years since 1982. And that is a good understanding of R squared. Make sure to have these written down right here, these interpretations, and you can use these like blank percent of the variation in the number of acres damaged by wildfires is explained by the years since 1982. If you look at the R squared interpretation we have on the screen, it's virtually identical to what they have, and you can just see blank percent of the variation in the Y variable, which is the number of acres damaged by wildfires, you can see it over here, can be explained by the years since 1982. And that's got it. Great job, everybody. Yeah, I don't really hear many people talk about the coefficient of non-determination. It's just the things that are, I guess, not determined by the model. It's just one of those things I read one time in a textbook, and I thought it was so cool. That R squared is the coefficient of determination. People don't even call it the coefficient of determination. Coefficient of non-determination, yeah. You don't really hear many people talk about that, just because people just say R squared. Or what does our model account for? What do we don't account for? And people don't use the fancy stat words because no one's going to know them. So just you read textbooks too much and then you read something. Well, that's got it. We'll be back. Connor, we need to talk more on Discord. And with that, I need to swing back by Knoxville. We'll be back right here later today. Swing by office hours. See you then, everyone. Bye for now. Bye. Grab some food real quick. Class coming up.